So welcome to IACS graduate student seminar. And today's speaker is Xiangyan, and she's a PhD candidate with SOMAS. And this is a part of her PhD dissertation. And she wanna, in the process of developing a modeling tool that can be used to inform fisheries management. So I just want to get her started quickly. And then her topic is unveiling the secret of a local estuary-marine ecosystem with modeling. Okay, all yours.
Thank you. Thank you, Yang, for the introduction. Hello, everyone. My name is Xiangyan. I am a PhD candidate working with Dr. Yang Chen at School of Marine and Atmospheric Science. Sorry. Today, I'm going to talk about unveiling the secrets of local estuary-marine ecosystem with modeling. For those who are not familiar with our lab, we focus on a variety of topics related to fishery science, such as quantitative fishery ecology, population dynamics, fishery stock assessment and management, and also ecosystem-based management approach. I need to timing myself. I cannot do now, but okay. And as a member of Chen Lab, my research focuses on ecosystem and habitat modeling. Before we started talking about modeling, I want to give a short introduction, a background introduction on some basic concepts. If you go to a fishery conference, you'll hear a lot of people talking about EBFM, the ecosystem-based fishery management. What is that, and why do we want it? As human beings, we obtain a lot of resources from the ocean. One of the most important resources is fish, which provides us important food and also protein sources. According to FAO report, global aquatic food consumption has been increasing and growing faster than all the terrestrial meat combined since 1961, second only to poultry. And in addition to this type of human exploitation, the ocean is also subject to a lot of pressure from climate change, which lead to a lot of changes within the ecosystem. In response to this pressure, some of the species have to change their diet composition, potentially due to the shifting distribution of their prey or predator. And some of the species are having to move out from their original habitats because their original habitats have become unsuitable for them to live or grow. And the increased CO2 has led to later blooming, which significantly influence the food resources of younger fish and therefore influence their survival rate. And some of the famous climate events, such as El Nino, were used to predict the changes in ecosystem composition and may influence the local economy. All these changes I just mentioned emphasize one thing, is that the within marine ecosystem is very complicated, and there are all the components are connected to each other in some ways. But due to lack of knowledge and resources, lots of our fishery management focus on single species, which means that we only look at the population size of single species that we cared about. But then we figure out that this is not enough, because this population size is also influenced by other species population size, like their prey and predator, and it's influenced by their the environment that they live in. Therefore, the concept of EBFM is proposed, for which we pay attention to multi-species and as well as the environment that the species live in. To achieve EBFM, we need ecosystem model to simulate the ecosystem dynamics and to get a better understanding of the overall ecosystem mechanism, which lead to the development of various types of ecosystem models. As our knowledge increase and more computational resources become available, the ecosystem models has become more and more complex and is more capable of simulating details and components of the studied ecosystem. So the Ecosystems serves as critical tools for achieving ecosystem-based fishery management because sometimes it's very hard to observe certain ecosystem interactions by just collecting data. And the traditional approach is struggle in evaluating ecosystem-wide responses to stressors. Ecosystem model can not only address these two challenges, but also is capable of simulating different management scenarios, which is essential for fishery management. So the type of model that we want to develop in this project is end-to-end ecosystem model. This end-to-end ecosystem model refers to models that represent the entire food web and also the associated abiotic environment like temperature, salinity, etc. And it requires the integration of physical and biological process at different scales. Here it emphasizes different scales because species at different trophic level has responses at different scales. Like for zooplankton, 1 week is a very long time, but for fish, maybe the time scale is more like monthly or seasonally. And this type of model should also be implemented two-way interacting between ecosystem components because we want to know how they respond to each other and influence each other. And this type of model should also account for dynamic forcing effect of climate and human impact at multiple trophic levels. So the study site of this project is Hudson River Estuary New York Bight ecosystem. The New York Bight ecosystem located in the middle of Northeast Continental Shelf, with species from both south and north coming into this ecosystem. And therefore, this region is considered as a transition zone on this shelf ecosystem. This region is under a lot of human pressure and also pressure from climate change. As the most important river in the New York State, the Hudson River ran into the New York Bight region, and it may extend the human impact along the river into the New York Bight through physical and biogeochemical processes. And meanwhile, the Hudson River estuary here provide a lot of important habitats for marine species in New York Bight. Lots of species use these habitats to spawn and nursery. Therefore, it's important to consider these two habitats together, and we want to better understanding how this ecosystem works and what the ecosystem dynamics looks like. So the overall objective of this project is to develop and test an end-to-end ecosystem model to quantify the Hudson River estuary New York Bight ecosystem from plankton to top predator by coupling the two submodels listed here. This model development process requires a lot of computational resources, and therefore the usage of seawolf cluster is necessary. Since the model development process is very time-consuming, we want to make sure that we are focusing on things. We are focusing on the right things before we started. So before building the model, we conducted a pre-analysis using statistical method listed here to investigate how different drivers might influence the overall ecosystem, which will help us justify our model configuration and also inform our scenario design. And here are the data sets that we used for high trophic level species, which are the fish species, those species that have bigger size that we can see eyes. We used survey data from Hudson River Biological Monitoring Program and the NOAA Bottom Trawl Survey. For low trophic level species, which I'm referring to the plankton species, we use the data obtained from satellite products and ECOMON project. The fishery-related data were obtained from related management agencies. So our analysis reveals that there are complex and dynamic connection within the ecosystem, both within and between seasons. The most interesting connection I'd like to point out here is the strong positive connection between the spring Hudson River ecosystem indicators and the fall New York Bight ecosystem indicators, which may reflect the critical role of Hudson River serving as an important spawning and nursery habitat for New York Bight. By conducting regime shift analysis we found that changes in ecosystem indicators are following the cues from climate change indicators instead of fishery indicators, which may indicate that instead of fishery pressure, environmental changes might be the primary stressors that regulate the ecosystem dynamics. So we further look into the temporal and spatial responses of the ecosystem. By examining the temporal responses of the ecosystem to warming temperature, we realize that the observed increase in richness is not solely attributed to the expansion of warm water species. How do we know that? If we look at the left figure here, the upper panel shows the trends of species richness, which we can see is increasing in recent decades. And in the lower panel, we have the community temperature index, which is an index that represents for the overall temperature preference of the community. If the expansion of warm water species is the solid dryer that lead to the increase of richness, we should expect that these two have similar trend, but they are not. And then we look at the spatial responses of low trophic level species and high trophic level species. And we found that they are having different responses. And within the high trophic level species, there is also difference between warm water species and cold water species. We also analyzed the species level dynamics by dividing species into warm and cold water species. We noticed that for lots of warm water species, they all moved northward, expanded into New York Bight with an increasing biomass. But for cold water species, there are kind of a mix of trends. Some of the species even moved southward from the north, expanding into the New York Bight. So a lot of things going on here. But the main takeaways for the pre-analysis is that first, warming temperature is the primary but not sole stressor that driving richness increase in the New York Bight. And second, we need to pay attention to species level dynamics and habitat connection within the ecosystem. And we also noticed that there were differences in how species responded to the stressor over time and across space. And therefore, the temporal and spatial scales matters. This work has been published recently, so if you are interested in more details, please feel free to scan the QR code here if you want to learn more details. Now that we have a basic understanding of the ecosystem, it's time to start working on the model development. As mentioned before, we're going to couple the two submodels here. The MOM6 cobalt model here simulates the dynamics of low trophic level communities, aka the plankton communities, and is developed and tuned by the Dr. Ross et al. In NOAA GFEL. This model provides distribution maps of 7 plankton species for the OSMOSE model. So even though we don't need to work on developing this part of model on our own, the model outputs are too big to be handled in personal laptops. Therefore, we used Globers to transfer the data to Seawolf and then process the data on Seawolf cluster so that the data is useful as an input for our OSMOSE model. Now let's shift our gear to the main submodel of this project, the OSMOSE model. The OSMOSE model is an individual-based and spatially explicit multi-species model. It's capable of simulating the whole life history of individual species, such as predation, reproduction process, etc. The key assumption of OSMOSE model is size-dependent opportunity predation. What does that mean? Now it's time to start the fun part. Let's go through some equations, some basic equations of OSMOSE. Here is the equation shows how OSMOSE model the predation process. In the left side of the equation shows the total prey biomass that's available for predator, which equals to the product of availability coefficient and the biomass of the prey. And then sum that for all of the prey available to the predator. And this equation only applies when it met with these conditions here. The prey size need to be within certain range. which is defined by the maximum and minimum prey and predator size ratios. Now that we know the available prey biomass to the predator, and the equations below here defined how much prey will finally be eaten by the predator. Here, there is a maximum limit for the predator to feed on the prey because you cannot just eat everything you have at one time. So to summarize, the size-dependent opportunistic predation means that predation will only happen under two conditions. First, the size ratios between the prey and the predator should need to be rational. Usually, bigger fish eat smaller fish. And second, the prey and the predator should encounter each other at the same location. They need to be overlapped spatially, both horizontally and vertically. So the predation process, the modeling of predation process is very straightforward in OSMOSE model, but also very important. To model the growth of species, OSMOSE uses the Wombat-Lengthy model. When the species eat enough of food, they will grow in their length and weight. And the amount of length that they grow is determined by the Wombat-Lengthy model, and the weight is determined based on the length-weight relationship. The two parameters here is basically determined by the shape of the fish. For those who are not familiar with Wombat-Lengthy model, it's a very classic growth model in ecology, where we estimate the length of species based on its age. So the fitted curves here the fitted curves usually looks like this. So the x-axis is age, and then the y-axis is length. So it basically saying that when the fish is younger, the growth rate is higher, and then when it gets old, the growth rate is gonna reduce, and at some point turns into zero, just like human beings. Another key life process is production, for which we want to know how many new eggs are introduced to the ecosystem at each time step. So this is determined by sex ratio, relative fecundity of species, and number of fish that are at suitable ages to be parents, and then the seasons for the species to spawn. For mortality, OSMOSE models several types of mortality, including fishing, starvation, and also other additional sources of mortality. For starvation, it's basically determined by the predation success rate of the species. So if you don't eat enough food, you might be starved, and you will go into the mortality module of the model. So fun time slips away so quickly. It's now the quiz time. Depending on what we learn, determining on what we have went through, can someone tell me in which case will predation happen in OSMOSE? Yes, please.
C.
Great, correct. So like the principal assumption of the model is very easy to understand, right? There's only two factors that we care about. The first factor is size ratio between the two predators. So bigger fish eat smaller fish. For this case, they're at the same size, so they cannot eat each other. And the second factor is that they need to be overlapped spatially. So for these two fish, even though this fish is bigger than that fish, they are not overlapping, so the predation won't happen. But here, we only can see their overlap, we can only see the overlap situation horizontally. How do we model the vertical difference? What if the fish live in different water layers? Even though they are having the same latitude and longitude, they are not necessarily really overlapping in water layers. So in OSMOSE, vertical overlap percentages are modeled through the parameter accessibility, for which we can describe how much two species overlap in water layers with different depths they live. To recap, in OSMOSE, within each time step, the model will first release the initial biomass of each schools and the low trough level maps, which is the plankton biomass at each grade, and then distributed them into spatial grids based on the spatial distribution that we provided, and then started to modeling life history based on the predation success. So for those who got eaten or cannot get enough food or was fished by human, they will go into this mortality module. And then those who are not who successfully survive, they will start grow, and some of them who reach the certain age will start reproduction, etc., and go on in every time steps. Now that everyone knows how OSMOSE works, and it's time to start build a model for Hudson River estuary and New York Bight. Assuming the model is a video game, these species are chosen to be the key players of the video games. Why were they chosen? So when we are determining the species list for an ecosystem model, we need to think about a lot of questions before we determine them. For example, which species are the most dominant species in the ecosystem, meaning that they are having higher biomass compared to other ones, so that they are contributing more to the ecosystem. And the other question that we might think about is, what is the key questions that we want to answer by developing this model? For us, as I mentioned before, we do care about the connection between Hudson River estuary and the New York Bight, and we want to know how they influence each other. So the species, most of the species here, they use both Hudson River estuary and New York Bight, and they have a very dominant biomass. So the species with the figure here are the species that will be modeled separately in the model. And for species who are in the table, they will be modeled as functional groups. By saying functional groups, I mean that they are having similar life history traits, so that they can be represented by similar parameters. So we can just like group them together and then put them in the model. This is because the model cannot handle like endless list of species. So we need to limit the number of species that included in the model. Now, species are determined. We should start collecting data and initialize the model. We first generate a grid map for the model, which defines the spatial domain and also the resolution of the model. And here is just a comprehensive list of parameters that we need to collect. For data like biomass and growth and length width parameters, they are very straightforward. We can get them from surveys, literature, and authentic website, etc. And for parameters like fishing and natural mortality, we can collect them from fishery stock assessment report, which are authentic reports for fishery management. And then we develop seasonal movement maps for all the species using biological surveys. As I mentioned, we need to know the spatial overlap situation of prey and predator, so movement maps are critical. And then the most difficult part of collecting data is to determine the size ratio between prey and predator. And what we did is we calculate the ratio between prey and predator by analyzing the diet composition data set. So we know that we have the average size of prey and predator, and then we got the size ratio between prey and predator. So we are now in the stage of model calibration. During this process, those unknown parameters will be set within a reasonable range based on available knowledge. And then the evolution algorithm and a hierarchical calibration approach will be employed to do the calibration. After the model is calibrated, we will then compare the model outputs with observed data set to evaluate the model performance, such as we can analyze the observed species biomass or the species size range, etc., etc. So the developed model can have a lot of applications, such as modeling the food web structure, conduct management strategy evaluation, evaluate the impact of fishery, migratory species, and climate change, etc. The model can also be incorporated into the fishery stock assessment process, which is a key way for incorporating scientific knowledge into fishery management. So in the left, it's the basic structure of how stock assessment process looks like. And in the right is the information that from end-to-end model that can be incorporated into the stock assessment process at certain stage. So this is a poster I presented at the World Fishery Congress last year, and it was supported by the IACS Student Travel Award. For next steps, we will work on conducting sensitivity analysis and exploring different scenarios. This simulation are all relies on the computational resources provided by seawall, because, for example, for sensitivity analysis, we need to run the simulation for hundreds of times for varieties of parameters. And we also need to do similar things for scenario analysis. All of these requires a lot of computational resources and can be done on laptop, but it's gonna take a lot of time for the computer to finish one scenario. So earlier last month, we submitted a new proposal for applying satellite images to improve our model performance for achieving EBFM. As mentioned before, now we are using the seasonal species distribution maps as inputs, which is the best available data that we can get from the biological surveys. So, but we do need finer spatial scales to simulate the ecosystem more realistically. So therefore, we propose to develop joint species distribution model, which will provide us finer temporal scale distribution maps of species. And how can we do that? To do that, we first need to develop a joint species distribution model, for which we need to test a tons of data set to select the most suitable data set that can be used for develop this distribution model. And we submit this part of analysis as a proposal to IACS seed grant earlier last month, or maybe late February. Thank you so much for coming today. I think I kind of went through everything so quick. Please feel free to reach out if you are interested in our research. And any questions? Yes.
You mentioned several times you need to go to Seawolf. What language is this written in?
Oh, yeah.
And does it run in parallel and scale? Tell me a little bit about the code.
Okay, so I forgot to mention this. So the OSMOSE itself is developed by Java, but they do have package in R. So when we are running the model, we are using RStudio. And then in terms of parallel, because so the model itself, when it's doing calibration, it's not necessarily parallel, but because we need to do a lot of simulation iteration. So like we need to do, say, if we want to do the sensitivity analysis on certain parameters, we may need to run the model like 100 times. So in this case, I think it's better to use, say, I was using the short call from a short call node from the Seawolf, so that I can run different scenarios at different nodes at the same time, right, which will save me a lot of time.
Perfect.
Yes.
I suspect the answer is yes, but the way you described it, any large fish that's in the same place, in the same depth as a small fish will eat it. Is that a universal sort of thing, or do some fish not like eating seafood?
So this is like the basic assumption of the model. So for this model, they don't consider the diet preference of certain species. They believe that like when these two fish, they met the size ratio and then they will eat each other. But yeah, but if like usually I think it's reflect in their distribution maps. So like if the fish does not like to eat fish, then it's maybe like it's usually appears in the surface part of the water layers. So it will maybe feed on the plankton species more instead of fish species.
Okay, so that might be wrapped up in the depth. I guess.
Yeah, yeah.
And,
Yes.
and also there's a diet data.
There is that.
The diet data, we analyze the diet data and then the information there, you know, what species intend to eat and what species. It's not like you make it up this.
No, I wouldn't think that. I just, it's a complicated problem.
Absolutely, absolutely.
I mean,
But a lot of assumptions.
yeah. Well, my naughty mind automatically went to, well, if we released a school of piranha, that would totally mess this up.
Yes.
So apologies if I missed this. When you were discussing mortality, I mostly saw mortality due to predation. Did you have other modes of mortality that you modeled?
Yes, a lot. Like one thing is the predation, and then we have the starvation mortality, which determined by like how efficient their eating, how efficient they're eating. And then we also have one very important part of mortality, which is the fishing mortality. So we do have a fishing module that you can input like the fishery landings for certain species, and then they will give an estimated fishing mortality for that species, like how many species, how many fish, how many biomass was extracted by fishery, etc., etc. And then they have other additional mortality source like the larval mortality and nature mortality, like those mortality that cannot be observed by our data. So they will, like during calibrated process, they will give an estimation of this value. Thank you. No problem. Yes.
I have a question about the trawl data sets that you're using. Are they only bottom trawls? And if so, how do you deal with that?
Yeah, so for the biomass part, we are using non-bottom trawl survey, and yeah, it does only contains like it does only use bottom trawl survey, but this data set has been widely used in a lot of ecosystem modeling developed here, including the Atlantic model that are applying to the Northeast continental shelf. So the data itself is considered to be representative enough for this ecosystem. Yes.
Okay, so this is your dissertation, right?
Yes.
And it seems like you've made good progress, so you're getting close to the end. It's up to your advisor, it may keep you here 10 years. But what do you want to do next? And how does this play a role?
Yeah, so this is only like it's the major part of my dissertation, of course, but we do, like in my dissertation, we also need to apply this model to certain scenarios. And what we want to do is use the model to explore the connection between Hudson River estuary and New York Bight to see, because in Hudson River, we observed that the sea level rise has led to the expansion of available habitats for marine species, like the spawning habitat is expanding. So we want to know like how this kind of change will lead to the ecosystem changes in the New York Bight. So this will be one scenarios that we are gonna analysis, and also like the warming temperature in the New York Bight is also part of this analysis. And then we also want to explore some other scenarios, but it's depending on what's the most important scenarios that stakeholders that want us to test about.
Looks like you want to stay here for longer than I thought. But again, I think that this is a really important tool, and there are a lot of organizations that actually, very interested in this tool. We already give a talk to, we have a project advisor committee that have stakeholders from state, federal agencies and NGOs. And, they want us to actually expand this model to cover the whole Hudson River system, go all the way up, cover the freshwater. And so we're close to finish the tour, then we're gonna work with the NOAA and state agency to test what scenario. What if we do this kind of management and how the system may respond to that? And so there's a lot of things that we can do if this is a tool that developed. And we really want to appreciate the resources that we have access to this institution, because otherwise we would not be able to do this kind of work.
So 12 years in grad school, good.
I think I should plan to graduate next year. So, yeah.
Any other questions? Any people online have questions? I think we're good. Okay. Thank you very much. Please grab